Hello everyone. Welcome to week 2 of the interactive sessions. So let us wait for a few minutes till some more people can join. Meanwhile, if you have any doubts, you can we can discuss those doubts. So we can start. So this week, a few new concepts are introduced in the lectures. So first of all, you got to see about this logistic function, the sigmoid function, and then we saw how to learn the parameters of a model. So parameters means you adjust those parameters to learn the underlying function between your input and your output. And then you also saw a new learning algorithm, the gradient descent. So yeah, are there any doubts in these topics, or do you want me to explain some part that from there? You can unmute yourself and ask.
Sir, could you go over the what is that? The multi-layer network of sigmoid neurons again?
Multilinear. Okay, sure.
Thank you, sir.
Let me share my screen. So is the screen visible?
Yes, sir.
Okay. Okay, so I think yeah, someone asked if calculators will be available. I think online calculators will be available in the exams. Uh, yeah, it will be there. So the topic we are looking into is multi-layer perceptrons. So, so the fundamental idea be yeah, sure. So this is not actually about week one or week two. If you have any doubts from week one, you can also ask this. So this is an open session. Okay. So the underlying theory that this for this we want to show in this is uh, the universal approximation theorem. So there is something called as a universal approximation theorem. So the universal approximation theorem states that given a large enough neural network, so that large enough will mean that you need more number of neurons, more number of layers. You can approximate any function that you want. So you would have a function of any shape, of any dimension, and then you can uh, use a multi-layer network of perceptrons to approximate or to learn that function. So when you talk about multi-layer perceptrons, till now you have seen these perceptrons, right? So you have just simple perceptron without any sigmoid activation. And so it was simply you take the sum of, so suppose you have three features, x1, x2, x3, and you have some output y. So y basically is plus one, say if your summation wi, so these are your wi's, w1, w2, w3. Suppose this is greater than 0, otherwise it is minus 1. So then we went to sigmoid or the logistic function. Say because we don't want your thresholds to be very hard. We don't want to say that at this point your decision becomes positive, at this point your decision becomes negative. So we want a smooth transition. So we came up with this, or we looked into this logistic function where you have these inputs x1, x2, and x3, and then you pass it through a logistic layer, and then you say that okay, your y is basically sigmoid of your x, summation wixi. So this just gives you a probability that what is your probability of you observing the output, and this output being of positive class or negative class or some other decision that you may want. So building on this, we now do a multiple we now use multiple layers of perceptrons, or multiple number of perceptrons. So say uh, we have a perceptron here, so a perceptron here. Suppose we use two perceptrons, right? And so now we have two perceptrons, and now what we do is we have, say, let us say we have x1 and x2. We have x1 here and we have x2 here. So this will go here, this will go here, right? And say this is your perceptron 1, this is your perceptron 2. So now you have, say, w11, 1, 2, 2, 1, 2, 2. and you'll have a sigmoid here, you'll have another sigmoid here, and then you'll get something else, and then it will propagate something like this, right? Or let us say we just combine them at once. uh,
Sir, I have a question.
yes,
So, if there are n neurons in the hidden layer, then there are
yes.
going to be 2 to the power n weights.
Why 2 to the power n?
I'm
Because,
asking.
okay, so if there are n neurons in your hidden layers, not necessarily. So, okay, so these are your n neurons, right? And suppose you have in the previous layer you have some, say, you have m neurons here. So each of these will be connected to n, right?
Yes.
So total number of weights is nm, n
Hmm.
times n. So basically you can represent these as a matrix. So suppose I'm talking about these weights right here. So you have two weights, we have two neurons in this layer, and you have three neurons in this layer. So now this is a matrix of, say, size. We are going from 2 dimensions to 3 dimensions. Let us think like that. So we'll have a matrix of size, say, 3 cross 2.
Okay.
Sorry, 3 cross 2. So you can write this as W11, W21, W31, W21. Okay, some 1, 2, let us see. 1, 2, and W3. So number of, yeah, so number of weights is how many connections there are. If you have some other type of connection, it will depend on that. Not 2 to the power n, but a multiplication of or product of these two terms.
Oh, thank you, sir. Thank you so much.
Yeah, is there a question? Okay. Hmm. So suppose uh, you combine these into one output layer here. So let us say this is some y. So this connection will also have a weight. Let us say h1, and this will have a weight, say h2. So earlier when we were talking about this single perceptron, we're talking about the output as being a single sigmoid layer, right? So it's something like this. This is so bad. So something like this. This is the output of a single perceptron, and this lies between 0 and 1. So that means, suppose this is the perceptron we get for this quantity based on some w and p. So our perceptron is basically, so sigma of w transpose x. So this depends, this w is a parameter, and depending on w we have something like this. So, so suppose this is it for this one, and suppose for this one we have some other singular, or you have some other sigmoidal or logistic function. So suppose it is something like this. Say w learned is negative, so it is something like this. So this could be something as I'm just showing this for uh, explanation. So that means if we train a neural network and say given two features, now we want to say whether your object belongs to class 0 or class 1, you can take a combination of these two neurons. So this red is the sigmoid for the first neuron, and this is the uh, sigmoid for the second neuron. And now based on this, you can say that, okay, if your data lies between, say, this and this quantity, your data lies in this region, then that means it is a positive class. If your data lies between this or this region, it is a negative class. So this is for two, when you have say two features or two neurons that you want to use. If you want more neurons, so this will have an extra dimension. So uh, or if you add more neurons, you will have more dimensions that you can use and say where your class begins or where your data lies in the positive or negative class. Uh, is that clear? Is that what you were asking? So hello. Lalita, is there a question? I'm not able to
Yeah,
hear.
hi. Can you hear me?
Yeah.
Yeah. So many places they say input neuron, but the input layers are not actually neurons, right?
No, they are not.
Yeah.
So
Okay.
when
Thank
we
you.
say about the input neuron, we basically say is the number of features that you may have.
Yeah.
The term
Only
is
those.
neuron, but that is not really
Yeah.
trainable. You don't do
Yeah.
anything on that.
Thank you.
This is just the you have so the terminologies is basically you have the input layer, then you have the hidden layers and the
Hidden
output
layer.
layers.
And, yeah. Some places they'll say that input layer neurons.
Yes.
So
So
just confirming.
yeah. So
Yeah.
because they use this term layer, they just say input neuron, but
Yeah.
they don't do anything on the input neuron.
Yeah.
It
Yeah.
just
Oh,
is not trainable.
thank you.
And inside this hidden layer, you will have a linear layer and followed by a activation layer or a nonlinearity. So uh, you may come across these terms when going through this some books or something. So these are some terms that I use.
Thank you.
Sir, I can't hear anything.
Yeah, so I'm not saying anything right now.
Oh,
Yeah,
okay.
any other question? So is this part clear what how these multiple layers help or what is the purpose of using multiple layers? Is that clear? I think.
What is the difference between the linear layer and the activation layer? Could you explain that
Uh,
again?
right. So let us go back to the first to a perceptron, right? So you have these inputs that you have x1, x2, x3, w1, w2, w3. And what we did was we did some summation of this. We sum over its wi xi, and then we apply a linear layer, or sorry, non sorry, an activation on top of this, and then we got back our output. We get some IM. So this sigma, it is applied on the wy or summation wyxi rather. So this part is called the linear layer because you are just doing a matrix vector type of multiplication here. So this is a summation here. So that is basically you are doing a vector multiplication or a matrix vector multiplication. So this part is called the linear activation function or the linear layer, you can say. The nonlinear part, you use this sigmoid type of operation. This is the nonlinear activation. So if you have looked at any code, you may see some other things like you might have seen ReLU or you might have seen 10H, and there are lots of options to use in this non-linear activation part. So so the basic power of neural networks comes from using this non-linear activation, because you see, so the main problem with perceptrons was that it was not able to learn XOR type of function, right? So it was not able to distinguish these type of problems. So you have, say, this, and you have this. You cannot make or you cannot do a classification or draw any hyperplane to separate this function. You need something like this, which is not linear, right? So if we had something like this, let us say if you had something like this, so you can just separate it using one plane, using one line. You can draw a line, you can learn some line, and then you can say that this side is negative and this side is positive. So drawing a line means you're learning a slope of a line. You're just learning these W's. So that can be achieved by one perceptron. You can just do something like this. You have x1, x2, w1, w2, and nonlinearity. And you can just say y is equal to plus or positive if this is positive, let us say, else negative. Okay, so this problem here is separable by a line. But when you have this type of problem, it is not separable by a line, because nowhere can you draw only a single line and then say that we have one so points on this side are positive, points on this side are negative. So what we do is we need some nonlinear function, right? Because there is no line you can draw here, you need a nonlinear function. So that is how that is where this use of nonlinearity or activation comes in. So if we want to relate it back to sigmoid, so I'll draw this again here. Okay. So so we saw this, like, so suppose you have two neurons. You have two neurons here, and you can combine, you can learn some weights over the two neurons such that you get a decision, or you get some sigmoidal function, something like this. So if you look at it, that is something like this, right? So suppose this is your layer where your output is negative, and this is the part where output is positive. So if you look at it, it is something like this. So this is your negative layer. So I'm representing this red by negative and this black by positive. So when you're at this region, your red, you're in the negative region, so your sigmoid is less than the threshold. And once you are in this region, say this region, you have some positive output here, and then again you go back to the negative output. So these two things are like correlated. So using a nonlinear function, you are able to simplify or simply classify this function, which was not possible before by a linear layer or just by drawing a line. So that is how why the non-linearity comes in, and that is why the success of neural networks was possible because of this non-linearity. So is that clear? Why do you need a linear, or what is the advantage of non-linearity? Because many problems are not separable linearly. You need some non-linearity to learn these non-linear functions.
Yes, sir. Thank you.
So here you might have seen something like this, like you are using multiple, you have some input neurons here, and then you use some, this is one hidden layer, and for now you are just adding or increasing the number of neurons here, but later on you will also see you can just stack different types of neuron on top of each other, and then you can get a output layer here. So the more neurons you use, or the more number of layers that you use. So for two neurons, you are getting a simple shape like this. If you had three neurons, you will have a this type of shape in the three dimension. If you're able to visualize something like this. So more number of neurons that you use, you will have more nonlinear function, and the more nonlinear a function is, the more you will be able to classify more and more complicated types of data. So suppose your data set is something like this. Let us say you have red here and you have blacks here. So even here you can just do let us say two-dimensional type of neuron can be helpful here, right? So you'll have in this region you'll have some, say x output is 0, class is 0, and here you place class is equal to 1. So even here you'll have something like this. But sometimes you may have data something like this. You have reds here, you have reds here, and all of these are your different class. So then you will need two bumps here. So you'll have a red bump here, a red bump here, and then these are all your uh, plus 0 region. So say this is your negative region, and this is your positive region. So you can have these more expressive type of functions when you use more number of neurons or more number of layers. And this expressivity comes because of using this non-linearity. Whether you use this logistic function or later on you look at say ReLU or something like that. Any more questions? Do you want me to explain any other thing? So did anyone try to implement the gradient descent algorithm? I think the code was given in the class or the lectures itself. So did anyone try to implement it? So the gradient descent is the most important thing that runs neural networks, you can say. So that is just a building block. You will be looking at a lot of other ways to make it faster, or you will see whether yeah, how to adapt it to different types of loss function that we have. So try and uh, implement it. The code is all basic code is already given in the lectures. Try and implement it and try to play around it, say different learning rates, different initialization. Try to plot the functions. So one, if you understand gradient descent, it will be very helpful. So optimization is the most important part of these neural networks. That is the main learning algorithm that you use. So try to play around with that code.
Sir, just to confirm, the reason
Yeah.
as to why gradient descent is used in neural nets is this to get an optimum set of like betas or w's or weights to minimize
Yes.
error.
Right.
Thank you, sir.
So yeah. So if you look at, so whenever you are given a neural network, how do you define a neural network? You need a couple of things, right? So this was also covered in the class. Let me repeat. So you need the data, you need your X and Y, because you want to train your model on your X to learn the function so that you get Y. So then you get us, they have a set of parameters. So this is your data. So W's mostly we represent it using W's or theta, and these are your parameters. Then a learning algorithm. So that is gradient descent for now. This is your learning algorithm. And finally, you have the loss function. So whenever you are training a neural network, what do you require? Or not also not training anything. So even when you're doing some type of learning, you want to evaluate, right? Am I learning the correct thing? Am I learning correctly? Is my algorithm going in the right direction? So how do you evaluate it? So that is where the loss function comes in. So the loss function tells, okay, if you're doing some updates, you are, and a loss function is decreasing, that means you are going in the correct direction. You are on the correct path. If your loss is increasing, which means you are not on the correct path, you are doing something wrong, or you need to change your algorithm. So what happens when loss is negative? Anyone? First of all, can loss be negative? And what does it mean for loss to be negative? Okay, if you think loss can be negative, just raise your hands. Or can loss be negative? Because you're decreasing loss, right? How much do you want to decrease your loss? Anyone? I hope I'm audible. Okay, those who think loss can be negative, so you can raise your hand. So there is this raise button on top. You can just raise your hands if you think losses can be negative, or if you think loss cannot be negative, then also raise your hands. Okay, so I think all of you think loss cannot be negative. Okay, yeah, right. Loss cannot be negative. So why can loss not be negative? Yeah, can anyone speak up? Why do you think loss cannot be negative?
We measure loss through ordinary least square, and that is a squared term. So squared though cannot be negative in
Yeah,
real.
that
No.
is yeah, that is correct, right? But okay, so yeah, that is true. You are doing ordinary least squares, then loss cannot be negative. That is true. But there are also other type of loss which we will come about later. So there is something called cross entropy loss, or there are some advanced type of loss. So yeah, whenever we use squared loss, it cannot be negative. But one more thing where we say the loss cannot be negative is because where does loss come from? So suppose uh, I'm saying my neural network is F. Let us say F is my neural network. This is my network, and my output is say F of X. So I give in some input. This is my output, or this is my prediction. And suppose my for an X, my true label is Y. So this is my true label. So when we are talking about loss given say some neural network F, my loss is some function. I don't know what that function is. So let me say that my function is phi. So some function of the difference between fx and y, right? So I will, so whenever my fx is equal to y, so that means for that point, my function has learned, or my neural network has learned the perfect set of parameters. Say if fx is equal to y, so that means I have no problem. In that case, my loss is 0 because we don't want to make any more changes. So our neural network has learned the perfect function. It has learned the perfect set of parameters. But if my fx is not equal to y, so then that means there is a problem. So then you are incurring loss. And so that is basically a positive thing, right? So the loss, if everything is learned perfectly, your loss is 0. Otherwise, you have some non-negative loss. You cannot have say negative. It does not make sense to have negative loss. So minimum that the loss can go to is 0, because that is when, so you have some loss of say 100, it goes to 50. So that means you are your 50% out of 100, let us say your 50 predictions are wrong and 50 predictions are correct, then it goes to 0. That means all of your predictions are correct. Now you cannot go further, right? Less than 0, so your loss cannot be negative. So that's a simple thing. Okay, so whenever you are training a neural network, so when we say we train a neural network, so like we saw, right, if we go to the sigmoid function again, so our predictions, so let me write this as y pred is a sigmoid. So suppose I'm talking about one perceptron neural network, very simple. So it is basically this. So suppose my true label is y true, and suppose I'm using a loss function of which is the mean squared error. So that means I want to measure my loss. It depends. So see, here this x is known, right? X is known, sigma is a function. The only thing that is a variable here is this w. So if you change w, your y pred will change. So that means this loss is a function of w here, right? And so because I'm using a mean squared error, I'll just say what is the difference between y pred and y true, and I'll just square it. Why I'm squaring it? It is because it is easy to differentiate square functions. You can just say this. It is easy to optimize this because square functions are basically of this shape, and you can optimize this well, because you will learn why this happens. So you will learn why this happens, because when you go deeper into other optimization algorithms. But basically these type of functions are very easy in some sense. You have already learned this type of function. So this is a square type of loss function. So now your loss depends on this variable w. So that is why this is called a parameter. So when we say we train a neural network, so it implies that you are learning the parameters. You're learning the parameters w, because this loss function will only change when, so y2 cannot change, only y pred can change, right? So y pred will only change when you change w. So when you train a neural network, that means you are decreasing the loss. You decrease the loss, and that means you are learning the weights. You're learning the parameters weights. So this learning thing, how do you update the parameters? How do you learn the parameters or learn the weights? You learn this using the gradient descent algorithm. So gradient descent algorithm, pictorially, if I have to show you. So suppose, for simplicity, let us say we have only one weight. So this axis shows us the weight, and this axis shows us the loss function. And we're using a squared loss, let us say. So my loss function will look something like this, right? Suppose, let us say. And now we know that this loss function is a function of w. So at some w, say w0, I have a loss of this much. So this is my loss at w0. So next, so now, where do you think, in which direction should my w, say from w0, I do some algorithm, I do some changes, do gradient descent, and I go to w1. So on which direction should my w1 be? Should I go left? Should I go right? So this is right, this is left. Which direction should my w1 be?
W1 should go right because we are trying to minimize the loss.
Right. So w1 should go right, right? So say let us say we get something here. So w1. So now we get a loss at w1. So now, as you can see, the loss at w1 is less than loss of w0. So that means the weights that you are learning, the weights that you are optimizing in the correct direction. Let us say correct means your loss is really decreasing. So suppose after some time you come to this point. Say this is, say, a wt. Now if we come to wt, should we keep updating the weights or should we just stop once we're in wt?
Then we should stop. We have reached the minimum.
Correct. So we should stop here, right? So that means we stop at wt. So that means we did some gradient descent, we learned the weights using gradient descent, and we arrived at wt. And now we will see that this wt is the final model parameters that we have learned. Final model parameters that we have learned. And then we will do the predictions. So we will now compute y pred using wt. So this t and this t are two different things, don't confuse. So let us say this is small t. So that is the optimal predictions and you can get. You cannot get better than this. So as you can see, even here we got to the minimum of the loss, but here the loss is not 0. So this is my 0 point, and here my loss is not 0. Say it is something, say 0.5, but that is fine because given this type of loss function, this data set and this type of weights, we'll get this as a minimum loss that we want. We cannot go beyond this. So this is how we optimize. This is why we need the learning algorithm. So using the learning algorithm, we update the weights so that we get to some loss, and which is hopefully the minimum. And I say hopefully because if our loss curve does not look as good as this, we may not be able to get to the lowest point. We'll be stuck at somewhere. So this is the aim of the gradient descent algorithm. Now, why this is called gradient descent? So because suppose we are at this point, at this point, at this point, I know that I have to go in this direction. So how do we go in this direction? Because we look at the gradient of the, so this is the gradient at this point, and we have to go in the opposite of that gradient. So at this point, we have to go in the opposite of the gradient. So at this point, we know that this is the minima. How will the gradient descent algorithm know that we have reached the minima? So the update step of gradient descent is this, right? So at any wt plus 1, we have wt minus some learning rate times gradient of the loss at wt. So given this, how will the algorithm know that we are at the minimum? What information can you get from this, that we are at the minimum point?
I think what happens is that, so
Yeah.
in the gradient descent,
Hmm.
what really goes on is that with each iteration we are progressively going down by like a certain fixed quantity.
Right.
Now, as we go further down and down and down and down, we ultimately come to a point where even with the iteration, the exact coordinates of the point where we are at, that doesn't change. So at this point, the gradient descent algorithm basically converges.
Yeah. So okay, you are mostly correct. So if you remember from your calculus classes, so whenever we are at the minima of a function or we are at the maxima of a function, the gradient at point is 0. At that point is 0. So once you get to this point, the gradient will be 0. So after this point, your gradient won't change much, even if you keep running your gradient algorithm, descent algorithm. So that is, yeah, like you said, that is how we know that the gradient descent algorithm converges, because once you reach here, there is nothing much to do. This will not update because this will get to 0 and your WT will not change anymore. So that is why this gradient descent is such a powerful algorithm. If you have a very good loss function, it will immediately try to find a minimum gradient, and then yeah, that is the optimal set of weights that you get. But the thing is, in neural networks, these loss functions are not so nice looking. You will have loss functions which look something like this, which are not good at all. So then you have some other techniques which will be covered in later lectures. So is that clear, the why how the gradient descent helps to find the optimal set of parameters and why it works?
Yes, sir.
Okay. Any other questions? Okay, so let us do a few. So let us look at this, right? So like I said, for neural networks, your loss function may be something like this, right? So that means if you start at this point, your gradient is non-zero. But if we come to this point, your gradient is zero in this case, right? So the gradient descent algorithm will think that it has reached the minimum, whereas the actual minimum is this point. So you will not get the correct set of, or the correct set of weights, or the optimal set of weights that you want. You will get some suboptimal set of weights. So you get a point where, okay, you are locally, you are at the minimum, but actually, so this is the global minimum that you want to get, and this is some local minimum that you want to get, right? So what can we, so can you come up with any, how do you think we can make sure that this does not happen, or how do you think we can mitigate this?
We change the step size to a bigger step.
Yes, we can do that. Can change the step size to a bigger step.
So it will take, it will go further
Okay.
towards right.
Yes, that is possible. But okay, so let us see what may happen if we take a very big step size. So again, coming back, so because so make note that at given some function, you are not sure how your loss function may look like. If your problem is good, if everything is good, it may look like this. But in this case, let us see what happens if we take a large step size. So again, let us come back to this problem, and then we'll go back to that. So suppose you are taking a very large step size. So suppose this is your W naught. Suppose this is your W naught. You are taking a large step size, and say at the next epoch or the next iteration, you are at this step. Fine, that is good. And now you take again you take a large step size. So you get to this one, W2.
Yeah, we get a zigzag pattern, so we'll have to again reduce it. So have a variable step size. Initially, we'll have to play around with that, I guess.
Yeah. So yeah. The intuition is almost, yeah, the intuition is correct. So if you have a very large step size, basically for those who are not clear about this, you will get to this point. So then the gradient descent algorithm will try to correct itself, and then it will come back to this point, let us say, and then again you will go back to this point. So it will
It'll just keep
do a lot
oscillating.
of, yeah, it will keep oscillating, and you will never get, not never, but it will take a lot of time to go back to this point or get to the minimum. So instead of this, what we can do, there is something called momentum, which will be covered in the later class. So initially you want your algorithm to be fast. So initially you use large step size. So from here you come to here, come to here, and then once you get close to the minimum, you decrease your step size. So now from here you want to go here, 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 and here. So this is where the concept of momentum comes in. So instead of ZD, there are some other algorithms called ADAM, which looks into this problem. So these things can also be helpful here. So here, if you take a large step size, so suppose this is your loss function. So suppose at once you go from here to here, once you go from here to here, and then you decrease your step size. Then you go to here, then you go to here, and then eventually you may get to the global minimum. So that is one way where you may be able to get the global minimum. But in most neural network problems, you will never get to the global minimum. You will rarely see problems where your loss gets to zero, but you can still get good results on testing data. even without getting the loss to zero. So getting the loss to zero is not always the priority. Getting a good set of say accuracy on the test result, that is more important. So you will get to the later lectures, you will get to reasons why that is so, why training a model to zero loss is not always favorable. Yeah, any other questions?
Hello.
Yeah, hi.
Yes. As you are mentioning that there is a local minima and there is a global minima, right? So
Yes.
basically, while developing the algorithm and when I am reaching to the local minima, how would I know that this is the local minima and there is another solution exists that is called as a global minima? So I mean,
So
it's a kind of a trial and error, right?
yeah, you cannot say if you're at a local minima or at a global minima. So if you say if you're running some algorithm for say 1000 iterations, and you see that after let us say 500 iteration you are stuck at the same point, and by saying I stuck at the same point, you will see that your loss function does not change. So suppose your loss function is 0.01 2 something like that, and after 500 iterations, after 200 iteration, again it remains at 0.01 or 0.012. So that means you are stuck at a minimum because you are not getting out of that. So stuck at a minimum means you are at some location, something like this, you cannot go out from this. So then it may be possible that you are at a local minimum, but whether that is a global minimum or not, we cannot say. So for that, you will have to run the algorithms a few more times and see what is the minimum that you get. So suppose the loss here is say 0.12. So if you run the algorithm again, you will get some loss which is say 0.003. So that means the earlier point where you got a loss of 0.12 was a local minimum, but now you are at a better minimum. So that may not still be a global minimum. It may, there may be other points where a global minimum may exist. So you cannot say for sure where you are at.
Okay. Okay. Thanks.
So we need to actually monitor the loss nicely, in the sense like whether it is, I mean, if we plot the loss function and keep checking whether, how you said, is it stuck at any point, or is it oscillating kind of, is it becoming too high or too low?
Yes. Hmm.
We take a decision accordingly, right?
Right. So you may have to rerun your algorithm multiple times to see
And
where do
for
you.
multiple epochs also.
Yeah, right.
Okay,
So
thank
that
you.
is why, yeah, even so, there is another thing called initialization. So how you initialize your neural network also helps. So suppose we are at this loss function itself. If you say if your initial, so because you are initializing the weights randomly, you are not saying that my W is 000 at initial point. We say that my W is some random numbers. And let us say that initially my W is at this point. So from this point, you see there is, it may get stuck at this point. But if you start at this point, if initially you are at this point, okay, if you initially you are at this point, it will be easy to find the minima. But if you start at this point, it may get stuck at this point. So initialization is also important. Where you initialize may decide where you end up. So if you are at a good initialization, you may end up at a good minimum, or if you say you initialize here, so you will just end up here. So that is also important. So there are various initialization techniques. and these are already inbuilt in the libraries, say PyTorch or TensorFlow. Any other questions?
There are these so many this ADAM and ADAGRAD and those so many algorithms are there for. So
Hmm.
how do we decide now which one to select or which one to start with?
Okay. So so basically the thing is, so there are various things: SGD, RMS pop, the meta
Mm,
grade.
yeah.
So that's where, so mostly in practice, like I like to use ADAM-W because that helps to converge, or that helps for a fast convergence. But generally, what you like to do is you try out with all of these things.
Try out. Yeah.
So
So with
yeah,
your experience,
yeah.
you can say that.
So there is this thing called hyperparameter optimization.
Yeah.
So so basically you run a loop. So at first you will use, say, SGT, and you run for a certain number of epochs. Then you
Mm,
use ADA to, or ADA grade to run a certain number of epochs, and
mm,
based on which set of which optimizer gives you the best validation loss,
mm.
you say that
Okay.
okay, I will take this as the, so you have, it is mostly a trial and error type of thing.
Mm,
But generally ADAM or ADAM-W are very good optimizers
okay.
because they
Thank you.
have, so like I mentioned, they have this nice computation of this momentum and this velocity terms. So it will be covered
Mm.
later, but yeah, those are nice things to use.
Another question I had regarding all these algorithms. I did a course which was like in depth. It was explaining all the math for all the add-on and integrate. But we will not be using those, right? So I did not quite follow like too much in depth. After a point, and then I quit that.
Acha. So you mean the computation of the momentum and all those things?
Yeah, correct. I mean,
Yeah.
ultimately, we'll be using
So
the
if
or
you're say,
mainly basically to know which parameter to tweak or how to adjust.
uh,
Don't know. In real life, I've not done so.
yeah, so for basic applications, you don't, so it's good to know, but rather it is good to have an ideas which term.
Mm,
So when you look at PyTorch Adam, you'll have something called as beta, you'll have
mm,
something called as weight decay. So it's
mm.
good to know what happens if you change
What
those
they?
terms, but it's not
Yeah.
that important to understand
Maybe
everything in
once,
detail.
yeah, once, even if you don't remember later. Mm,
Uh, so you can just have a thing that if I change
mm,
beta, what could happen or something like that.
And what exactly is beta?
Right. Yeah. So for, yeah, if someone is going into research, he or she has to
They will know. Okay.
understand it. But for applied, you don't. That is not
Mm,
that necessary.
mm. Thank you.
So excuse me for a few minutes. I'll be back. Yeah, I'm back. So yeah, any other questions you want to discuss? Any doubts? So hopefully everyone understood the gradient descent algorithm. So that is very important. And yeah, so you will come across, I think you might have gone through back propagation. So back propagation is basically a derivation or a expansion of, you can say, the chain rule that we use in differentiation. So that is useful when we want to compute the gradients, uh, like, gradients with respect to the loss. That is, how much does the weight change with respect to the loss, or how much does the loss change with respect to the weights. So that's where back propagation algorithm comes in. So I think it will be covered in the next lectures.
Sir, what are those tower functions that were being discussed in the penultimate lecture in module 3.5?
Okay, let me check tower functions. Okay, let me check. Can you module 3? So I think that was the okay. Hmm. Oh, it is something like this. So you want to approximate. So this comes from this universal approximation theorem, right? That you have some function. You have suppose this function, and now you want your neural network to learn this function. So obviously neural network cannot learn such a curved function. So you saw that for let us say for one perceptron, you will have that uses a sigmoid layer, you will have something like this. And if you use two perceptrons, then you can combine these to get something like this, right? So if you have lots of these perceptrons, you will, so suppose the shape can be like this, the shape can be like this, and so on. So if you combine a lot of these perceptrons, you can have any desirable shape. So if you look at this function, so you can just say that this is the combination of this tower, then this tower, so this and this tower, so this and this tower, and so on. So like this part is this tower, say this tower, and so on. So this is basically you are trying to learn this or learn this continuous function using discrete steps, using these tower type of things. So these towers come from combination of the sigmoid functions. So if you vary the height and weight, you'll get this. So let me share the screen. So wait a minute. Hmm, let me share this. So is this visible? Is this
Yes,
visible?
sir.
Okay.
Yes, sir.
So let me show you an example. Ah, so look at this simple example. Let us say this one. Hmm. So you have some X here. You have some output. This is your perceptron one. This is your perceptron two. Then you have two hidden weights, and then you have this. So using two perceptrons, you are able to get the function, this rectangular type of thing that you see here. So if I increase this, so see it moves to the right. If I increase this, it moves to the right. If you decrease this, it moves to the left. So if you make this small enough, so that means you can move this around. So if I change the height, this will also change. You can change the height, you can change these weights. So this depends on how your weights are calculated. So we saw about gradient descent, right? In gradient descent, these weights, your heights, or these hidden layer weights are changed. So when we say they are changed, so suppose this is changed, your function will look something like this. If this increase, your function will look something like this. Now, when you combine a lot of these, you'll get something like this. So Now you see there are four, right? One, two, three, four. So for two you get one rectangle, for four you get two rectangles. So this is one rectangle and this is one rectangle. So let us say I change this. So this one became smaller. Now let us say I change this, I increase this, or I increase, I mean your gradient descent is trying to learn this. Suppose this is updated as this, or this is decreased, and so on. So if you change these parameters, or if gradient descent changes these parameters, the shape of these functions that are learned will also change. Now suppose you have a lot of these neurons. Say here, I don't know, 10 or more than 10, I think. Yeah, 10 neurons. So for 10 neurons, you will have just one, two, three, four, five buckets or five rectangles that you have, and you want to change this. So I will change. Okay, these are not changeable, but you can change the heights here, say this or this, and so on. So you want to approximate this function, right? So this set of heights is not able to approximate this function. So okay, so this website is let me share the link in the chat. So there is this website called neural networks and deep learning.com. So now I want my this height to be small, list, right? So because now let us think in terms of a neural network. So at this point I want, so is my cursor visible? Ah. So at this point I want my output to be here, but my output is here, right? So this is my loss functions, a difference between this and this. So I want this to come down. See, now I want to this to come down. Now if I want to reduce the loss here, once I reduce the loss here, you can see the height. So this is a learnable parameter, this is changing. If I reduce the loss, the height is changing, right? And now I want this thing to be these are not adjustable, but I thought this should be adjustable. Okay, I'm just adjusting the heights for now. Again, I want this. So the loss at this point, the output should be say less than -2, but I am getting output of 1. So again, there is a loss. And now I'll try to reduce this loss. That is, I will try to push this function down. So that means this parameter is also getting updated. So this is gradient descent that is working, right? So I have a loss or deviation of say 0.62. So here I would like this to go up. Here I like this to come down. Here I like this to go up. So my loss, so you see, if we try to decrease the loss, these variables will also change. So that is how the learning happens. You evaluate the quality of the network that has been learned using the loss function. Now once you evaluate that, you will see how your how gradient descent should work. So based on that, it will update the weights until you get a minimum loss. So these things, so you cannot learn this curvy thing with a neural network. You can just approximately learn it with different number of towers. So if you use more towers, you have smaller and or thinner and thinner towers. So like we saw here, you can make this thin. So like if you have a lot of these thin towers, then you will have a better approximation of this loss. So these are the tower functions. And similarly, this happens for more than the 2D case also. In 3D case also, you can combine a lot of these things. And yeah, so that is what is shown in that. Those are the tower functions. Hope that is clear.
Sir, another question.
Hmm.
So, could you go back to that previous bit with that really large neuron, like that really large set of neurons stemming from
This one,
one input?
this one.
Yes, yes.
Ah,
So, what exactly do the points, what exactly do those numbers in the hidden layer circles represent, and what does H represent?
Okay, so these numbers they represent, so like I said, right, for each perceptron you have a linear layer, and following the linear layer you use a sigmoid logistic function on top of that. So when I
Yes.
say this is 0.2, so that is the output of the logistic function. So there was some input, say from X to this one. So you did something like W times X on that thing, and then you applied a logistic function on top of that. You got 0.2, and now this neuron is connected to this one. So this H represents, in some sense, your height or your weight of that connection, how much weight. So they have not shown all of the weights, but basically it says how much should. So this was layer 1 weights, these are layer 2 weights, hidden layer weights. So these H's are the representation of the hidden layer weights that you have.
Can you calculate these hidden layer weights?
Yes, we can calculate these hidden layer weights. So this is a big network, but for a small network, you have to write down each and every weight because we know the expression. So let me share this screen. Little bit. Oh, signed out. Yeah, so suppose you have a small neural network, something like this, and let us say some output here. So you have x1, x2. So this is your, say, 1, 2, h1, h2. Let us say something like this. And this is your w11, w12, w21, w22. So at, say, at neuron 1, you will get something like w11 x1 plus w21 x2, and you will do a sigmoid of this, right? So here the 0.2 that you were looking at, so maybe this is 0.2, let us say. And now from here to here you will have, say, h11, and here you will have h12, then here you will have h21, here this weight is h22. So if I want to look at what I get here, so let us say this is, let me say it is A1. And similarly, I get some A2 here. So at, at this node, what I get is this. H11 times A1 plus this H21 times this A2, and a sigmoid of this. Let us say this is, what do I say? Say A1 head. So here I will have some A2 head, and then I will have some other weights here. Let us name this as C1, C2. So my output will be C1 times A1 head plus C2 times A2 head. So this is my output. And now I suppose my actual or true label was Y true. Now my loss is Y true minus C1 A1 head plus C2 A2 head. Sorry, C2 A2 head. So this is my loss that I get. And based on these loss, I will try to change. So what are the things that can be changed here? So x1 and x2 are fixed. These are your inputs. They cannot be changed. But all of these things, w1, w2, all of these weights, all of these things can be changed. So based on the loss, I will try to change these H1, H2, W1, W2, all of these things. How I change this? There is this algorithm called backpropagation, which will come about in a future class. So that is how that when I say training happens, these W1, W2, H1, H2, C1, C2s, all of these things will be updated. So that is how. So for small networks, it is easy to write it down. For large networks, it is a bit tiring to write it down because you'll have a lot of these combinations. So that is how the learning happens in neural networks. Is that clear?
So can I just confirm like my understanding of this?
Yeah, go on.
Yes. So basically we do one round of logistic function calculation in the first uh, input. I'm calling hidden layer 1 as H1,
Yeah,
or
right.
let
Yeah,
me just
this
call it
is H1.
L1 because H is a separate thing. So
Okay.
between input layer and L1, we're doing
Hmm.
one round of this cal this logistic calculation
Yeah,
using weights W11, W12, W21,
right.
W22, like that.
Yes.
Then we are going from L1 to L2. We're doing another
Yes.
logistic function calculation using the outputs of that previous one.
L1. Yes.
Hmm. And out here we are using like the H11,
Mhm.
H12, H22,
Yes.
those as weights.
Yes.
And then finally we are doing C1A1 plus C2A2 to get the
Yes.
output as
Right.
Y pred. And then loss
Yes.
function we're calculating as Y true minus Y pred.
Yeah. Correct.
Thank you
So
so much, sir.
yeah, this is the main thing. So this when you are going in this direction, this is generally called as a feed forward network because we are just going forward. And then once we get the loss, we have to train these weights, right? So that algorithm is called the back propagation because we get some loss and are propagating it backward to learn the weights. So that is called back propagation.
Could you clarify the difference between feed forward and back propagation again?
Okay, so when we are going from the input layer to the output layer and doing this calculation, that is the feed forward computation. Once we get this loss after doing the feed forward computation, we have to update the weights. How do we update the weights? Because we have some information that okay, my weights are not so good based on the loss that I get. So I have to give this information back to the weights, right? That okay, how much do I need to change the weights so that my loss becomes good? So we have to back propagate this information. So using the information of the loss, you back propagate towards the weights. So back propagate goes from the output layer to the towards the inward input layer. So that is why I'm drawing it in this direction. So that is back propagation. Using the loss, you try to learn what are the weights that should be so that your loss is decreased. Then once you get the updated set of weights, again you do a feed forward, you check your loss, and then if your loss is not very good, you again do a back propagation. So you repeat this process until you get a good set of good loss function or good loss value.
Okay, sir. So feed forward is basically calculating that Y pred value, that
Why?
C1A1 plus
Yes,
C2A2 from the initial
right,
input. But
right.
then now we see we like do loss function on it. And now from the
Hmm.
loss function, basically we see this one. What is that? We now see which parameters, aka weights, we have to update. And
Change.
that
Hmm.
information, when we pass back through computation, that is the back propagation. And now we do
That,
repeated
yeah, right.
iterative loops of feed forward and back propagation.
Correct, correct. Yes.
Thank you, sir.
Okay. Okay, so how do you decide the number of neurons? So that again is a hyperparameter tuning. So you train your network with some number of neurons, say 10 neurons, you check your result. Then you again run with say 20, run with 30 and check different results. And based on the base setting that you have, you say that, okay, suppose at 30 neurons, you get the minimum validation loss. will come to what is validation loss later. So whichever setting gives you a better result, you choose that as the number of neurons. So this is termed as hyperparameter tuning, because there are a lot of hyperparameters. So there can be questions like how do you set the learning rate in gradient descent? How many layers do you want to use? How many iterations do you want to do your training? How many neurons do you want to use? So all those questions, all those things are hyperparameters. So you do hyperparameter tuning to see which setting or which configuration gives you the best loss, and then say that okay, this is my neural network.
Sir, could you show that previous slide again where you explained feed forward and back propagation and that calculation? It's really good. I want to take picture of that.
Okay, I think this one, right? uh, is this the one?
Yes, 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 sir.
Yeah.
Okay, sir. Thank you, sir.
Okay. Is there any question, Lalita?
Yeah. So here in this same diagram, feed forward, when you
Ah,
are actually implementing, uh, so your first step will be you are doing the summation, which is that linear step, and then uh, you apply that. Then you again there'll be another step uh, on that will be
yes,
your activation function, which is sigmoid here. So it will be
right.
like a two-step thing, right?
Yes. Mm,
Some places they show that, I mean, not like a layer, like in as a block diagram. So in between, they'll show that activate, it is passing through
yeah,
the
yeah.
activation, and then, yeah, that
They
gets
show something
confused,
like
like,
this.
yeah.
Mhm. So you will have some. So in this layer, you will have some say H. After this, you will get some A. So this is called as pre-activation, and this is called an activation.
Or inside one same neuron
Mhm.
representation.
Yeah. So you will see later that when you do back propagation, you will need to differentiate with respect to this, as well as you
Mm,
need to differentiate it with respect to this. So these
yeah.
both of them are required.
Mm.
Okay, thank you for attending to this session. We will meet again next Saturday. You can leave if you have no more questions.